everybody, welcome back to chemistry. And so now we are going to go over one more periodic property called ionization energy. And so first, let me give you a definition for that. So ionization energy, otherwise known as IE, is the energy needed to remove the electron in an atom that is furthest from the nucleus and send it flying off into space. You will see that ionization energy is a periodic property in the sense that when you're on, say, the left side of a period, what you'll see is a relatively low ionization energy. But then as you go across the periodic table, you will see that that ionization energy slowly increases. But then you go to the next period, the ionization energy is even a little bit lower than the element before it, but it starts increasing as you go across the next period of the periodic table. Okay, so first, let's go ahead and write out some pictures to describe how ionization energy might affect an oxygen atom. So I'm going to write oxygen here. And oxygen's, its symbol is O. So what I'm going to do is I'm going to draw a quick picture of a neutral oxygen atom. So you can look up its atomic number is 8. So that tells you that the oxygen atom has 8 protons or 8 positive charges in its nucleus. And then we have 2 electrons as first energy level. I'm indicating electrons with negative charges here. And then also what we have in the second energy level is we have 6 electrons, like that. Put negative charges here to indicate that. Okay, so let's do an accounting of this neutral oxygen atom. So this is a before picture. And so the accounting suggests that we have 8 positive charges. We have 8 negative charges, and so you can see we have as many negative charges from the electrons as positive charges from the protons, and so this can be considered a neutral atom. Also, I should note, this nucleus not only has 8 protons, which are positively charged, it has some number of neutrons, and we don't have to worry about neutrons in this accounting because neutrons have no charge. Okay, so let's describe what happens in ionization energy. What happens in ionization energy is you hit the atom with energy. And so I'm symbolizing here energy with a wavy line. And you strike this atom with energy. So this is E. And what happens if you have enough energy, an electron in the highest energy level of the atom will just be kicked off the atom and fly off into space, like this. Just flies off into space like that. So let's go ahead and indicate that the electron is falling off. So that is our before picture. Now what I'm going to do is I want to draw an after picture for what this looks like. So the after picture is we're going to show what the oxygen atom looks like when we pull off this electron here. And so now I'm going to write after here. So in this after picture, we haven't changed the proton number, right? So we still have 8 protons. We haven't changed the number of electrons in the first energy level. Looks like this. However, instead of having 6 electrons in the second energy level, we only have 5. So let me draw that. So now we just have 5 electrons in the second energy level like this. Okay, so now let's do our accounting in this after picture. Oxygen still has 8 protons, but if you count the number of electrons, you will see now we're down to 7. And so it has 7 electrons, and so it has 7 negative charges. So what that means is this atom is no longer neutral. The 7 electrons, each with a negative charge, can only balance out 7 of the 8 positive charges from the protons. So I think you can see that here, this is not a neutral atom. This is an atom with an extra positive charge. Whenever you have an atom with an extra positive charge, it is called a cation. Okay. Now, what I'm going to do is I'm going to try to take this picture and make it look more like an equation. So we have the before picture. I'm going to draw an arrow here, and we're going to an after picture. And to complete this after picture, we have here what remains of the oxygen atom once you remove one electron. But now I'm just going to indicate a plus here that there is an electron here that's been flying off here. And so I can put a dot here and a negative sign for the electron, but usually chemists don't like that, and so they're going to indicate an electron like that. Okay, so let's take this equation and put it in terms of symbols. And so we have an oxygen atom, its symbol is O. If it's neutral, there's no charge associated with the O symbol, it's just oxygen. And so we hit it with energy, and what you can see now, after you remove one electron, it is missing an electron, has an extra positive charge. If it has one extra positive charge, we indicate that with a single plus like that. So whenever you see an elemental symbol and it has some kind of plus, here it's 1 plus, but if it's missing 2 electrons, it'll be 2 plus. If it's missing 3 electrons, it is 3 plus. Whenever you have a plus sign, this means that this oxygen atom is not a neutral atom, it is a cation. And so to complete the equation, I'm going to write plus electron like this. What I want to do is I want to add another term to this equation. You might often see it like this. It's the same equation like this, but a lot of chemists like to indicate here with ionization energy, what you're doing is you're adding energy to the neutral atom that you have before. So to indicate that, we're saying energy plus the neutral oxygen atom will give you the cation plus electron. Now, what we can do is we can sort of generalize these equations. And the reason we might want to do this is because this process of removing an electron from an atom, you can do it for any element in the periodic table. So what we might do is generalize the process with an X. So I'm just going to generalize this first equation here. So it's a neutral atom X, there's no charge, and then we get X with a positive charge because we're missing electron ionization energy, and it's going to release the electron. Now, if we want to, we can add in an energy term like this to indicate that an ionization energy, the neutral atom is absorbing the energy, producing the cation and the electron. Okay, so what I'm going to do is I'm going to erase this, and I'm going to draw pictures for another atom really quick, which will be sodium, and I'll quickly describe that. Okay, so I finished my pictures for a description of the ionization energy of a sodium atom. So here is sodium. The sodium atom, as you can see, is a larger atom than oxygen. And the reason is because its atomic number 11, and so it has 11 protons and it has 11 electrons, and that's the neutral sodium atom. So let's talk about where these electrons are. But first, here are the protons in the nucleus. There are 11 of them. There's going to be some unknown number of neutrons. Now, we have to account for sodium's 11 electrons, 2 in the first energy level, 8 in the second energy level, and then that's 10 right there. And then we have a last one in the third energy level. And so here is the accounting here of the neutral sodium atom. And you can see there is many electrons as protons. And so its symbol is going to be Na. And it's not going to be Na plus or Na negative, just Na. All right. So what we're going to do is we're going to hit this atom with energy. So here is the energy. It strikes the atom like this. So this is the energy. And what will happen is you're going to pull off the electron that's furthest away from the nucleus. And the reason is this is the electron that is most weakly held by the nucleus. The other ones are more tightly held. So this electron goes flying off. And so now we have after sodium. So you can see sodium now is missing 1 electron. It still has its 11 protons, but you're now down to 10 electrons. And because of that, it has 1 extra charge. And now the after sodium is a cation. It has a positive charge. And you can see, to complete this sort of picture, I indicated that we have an electron here flying off into space. And so again, the after is the sodium with a positive charge. Okay, so what I'm going to do now is I'm going to erase this picture and I'll get back with you. Okay, so now what I want to do is talk about the values of ionization energies for atoms and show you that this is a periodic trend. So you can look up the value for the ionization energy of oxygen, And what you'll see is if you're trying to remove the outermost electron from oxygen, it requires a relatively large amount of energy. It's about 1,300 kilocalories per mole. Don't worry about the units right now. Just see that this value is relatively large for oxygen. But for sodium, you can see it has a different value. It's much less. It looks to be about a third that of the value of oxygen. And so its value is only 496 kcals per mole. But again, ignore the units, let's just look at the number. You need to understand why sodium has much less value of ionization energy than oxygen. And it's actually a pretty simple reason. The reason is this. You might remember oxygen is a smaller atom. And sodium is a larger atom. So let's think of the implications of this. So if oxygen is a smaller atom, so the electron that you're trying to pull out from the highest energy level is pretty close to the nucleus. That attraction of the electron, because it's kind of close to the nucleus, is pretty strong. And so you're going to need a lot of energy to knock the electron off. Now, sodium is a much larger atom, and the reason is you have an 11th electron, and that goes in the third energy level. That electron is much further away from the nucleus, and so its attraction from the nucleus, the positively charged nucleus, is not as great. So you don't need as much energy to do that. So let's go ahead and increase the slide on this periodic trend for ionization energy. And so what I want you first to notice is that this is an abbreviated periodic table. And so on the left side, we have the S block here, and on the right side, we have a P block. And another thing I want you to notice, here is hydrogen here, where you might expect it, but some chemists like to put hydrogen over here in group 7 because in many ways its properties are similar to the halogens, but we're just going to forget about that right now. So what I want you sort of notice is, first off, where is oxygen in the periodic table? It is here, and there is its ionization energy, about 1,300 kcal per mole, and then here is sodium. So one of the things I want you to notice as you go across a period of elements, the value of the ionization energy slowly increases. But then when you go down a group, the ionization energy drops. So when you go from the second period of lithium to the third period of sodium, its ionization energy drops. But then from there, as you go across the period, it increases up again. So you need to know why that is occurring. And so it's really kind of easy to understand, is that the value of ionization energy is sort of inversely related to the size of the atom. So let's look at this picture, remind you what the sizes of atoms look like. So first off, we want to understand why, as we're going across a period here, that the ionization energy increases. So that, again, is pretty easy to understand, but let me write here, this is ionization energy increases. There we go. So look where the electron is in these atoms that you're going to remove. If ionization energy, you're always removing the electron that's furthest out. So with lithium, it's there, but beryllium, the electron you're going to remove will be closer to the nucleus, and then boron is closer still, and carbon, and neon, it's extremely close. And so here, as you go across the periodic table, the electron you're trying to remove gets closer and closer to the nucleus, so the attraction gets stronger and stronger, so you're going to need more energy to remove the electron. So why is it as you go down a group, the ionization energy decreases? It's for a similar reason. So with lithium, the electron is there, but sodium, the electron is further out to the nucleus, and with potassium, it's further out still. And the reason why, you might remember as you go down a group, what you're doing is you're adding a lot more electrons as you go down the group, and so those electrons go into a higher energy level that's further out. And so as we go down a group here, that electron we're trying to remove gets further and further away, the attraction is weaker and weaker, and so it's easy to remove, so we don't need as much energy. Okay, thank you for listening to that. We'll see you next time.